Hello guys and gals, and welcome to part 3 of section 5.9. I just rewrote what we stopped with in the last video, which was setting the rate law for the appearance of NO3 equal to the rate laws for the disappearance of NO3. And that's all that we had done, and we're doing this because the steady state approximation says if we know this information, we can use it to solve for the overall reaction's rate law. So let's do the same thing with the rate law for NO. NO is also one of our intermediates. So let's go back and let's look at the steps here. We can see that NO, thankfully, is only produced and consumed in a single step each. So it's produced in step 2 and it's consumed in step 3. So we'll only have 2 rate laws, and I'm just going to go ahead and set those equal to each other because we know they're going to have to be anyway. So the rate law for when step 2, or for when NO is produced, is the rate law for step 2. And the rate law for when NO is consumed is the rate law for step 3. And there we go. We're going to save this because really what we're going to do next is we're going to look at that rate law that step 2 said should be the correct rate law for the overall reaction. Now we know that it is not correct because it has the concentration of an intermediate in it. We need to try to see if there's something that we could replace that concentration with, and it just so happens there is. We can take this equation right here that we just found, the one where we put the rate of appearance of NO3 equal to the rate of disappearance of NO3. And we can rearrange it so that it solves for the concentration of NO3. So, let's do that. We'll put NO3 out here. We'll do some quick algebra, and we'll see that that leaves us with K1 times the concentration of N2O5 over Kr times the concentration of NO2 plus K2 times the concentration of NO2 plus K3 times the concentration of NO. So all we did is we took this the equation where we had set the rates of appearance and disappearance equal to each other, and we rearranged that so that it's solving for the concentration of NO3. Now what we're going to do is we're going to take this, and because it is equivalent to the concentration of NO3, we're going to replace it into what should be the correct rate law. And so what we'll end up with is going to look like this, where rate is equal to K times what's taking the place of the concentration of NO3 and all of that, of course, is still multiplied by the concentration of NO2 because we haven't done anything to get rid of that one yet. But what we can hopefully see here is that NO2 would be considered to be on the top of a fraction out here, and it's on the bottom of a fraction here. So we can cancel out one of the NO2s just because they're opposite ends of a fraction. So we can cancel those out. So that actually leaves a rate law of okay, so we replaced the concentration of NO3 with a rearrangement that was used to solve for the concentration of NO3 based on the rates of appearance and disappearance of it. Then we canceled out and combined like terms, and we're left with the rate law for the overall reaction should be rate is equal to K times K1 over K1 times the concentration of N2O5 over Kr plus K2 times the concentration of NO2 plus K3 times the concentration of NO. Well, we again know that that cannot be the correct rate law. Why? Because it has the product in it still. NO2 still cannot be a part of this rate law, and NO is just another intermediate that we have put into here that we cannot have. So if we go back to the notes, I've put it out pretty plainly in the notes written out what it is that we're supposed to see with the math. So we'll go on from there. We are obviously going to have to rearrange we're going to have to do the same thing where we took the rate of appearance that was equal to the rate of disappearance for NO, and we'll rearrange it to solve for the concentration of NO, like we have right here. So once we go through and we cancel out all our like terms, we will replace concentration of NO with that rate law, where we solved for the concentration of NO using the rate laws above. That's going to leave us with several things that we can cancel out. We'll be able to cancel out the NO3, which we should not have in there anyway because it's an intermediate. We'll be able to cancel out the NO, which we cannot have in there because it's the intermediate. And we'll even be able to cancel out the NO2, which we cannot have because it is the product. That will leave us with a bunch of K values and the concentration of N2O5 to the first order. Now, because the original K value is made up of all the other K values, we can just say our rate is equal to regular K, understanding that K is equivalent to all of the other K values set up in that fraction that we see them above, and times the concentration of N2O5 to the first. So it was a really long and complex way of saying we've got to make sure we account for equilibrium, and we've got to make sure that we do not use equilibrium to determine rate law. Okay. Now, this is as many videos as I'm going to do, but we will definitely talk about this more in class, so please